All right, so the fifth talk for this session, it's Luigi Portinale, and the topic is exploiting data mining for authenticity assessment and protection of high-quality Italian wines from Piedmont. Great.
Okay. Good afternoon, everybody. I'm Luigi Portinale. I'm professor at the University of Eastern Piedmont, and I'm going to talk about a data mining approach to the assessment of authenticity assessment for high-quality Italian wines. I know that it's much more fun to taste wine than talking with wine, but however, we are just to be satisfied with talking today. The work is a joint work with some researchers from the food chemistry area, and they are the enological experts, and we were the computer science counterpart trying to show how state-of-the-art data mining techniques can be exploited to this kind of problem. And the outline of the talk is the following. I will go through a brief introduction to the problem, and I'm going to set the problem into a project that is called Tracos Wine, which is a project that has been funded by the regional government of Piedmont. And I'm going to describe how we collected data and we prepared data for this kind of task. And then I'll go through the data mining characterization of the problem, where we have to determine which kind of problem has to be solved and which kind of analysis has to be performed in order to solve the problem that we have. We deal with two different categories, with three different data sets. And in a first data set, we were dealing with the complete feature set that were available after the chemical analysis. And we also had some data sets that will be produced by exploiting feature selection methods in order to reduce the number of features available for the task. And I'll go through some conclusion at the end. Okay, the problem is to try to authenticate wine and to protect wine from fraud detection. The problem is a very big problem because wine adulteration may produce health problems. However, we are not essentially, let's say, we don't want to deal with specifically with the problem concerning health, but we have to deal with some other aspects in wine adulteration, which is the economic damage that can be produced by adulterating wine. In particular, it is estimated to be almost 7% of the whole wine market is involved in this kind of adulterations, and this means several millions of euros or dollars, if you want, for each year. So it's a big problem, and to detect the fraud is very complex. It's very complex because we have complex chemical profiles that come from the analysis of the wine, and such chemical profiles very often are influenced by different features that are not very well defined. For instance, one of these features is the terroir influence. Terroir means the soil on which the grapes grow, and then the specific feature of the soil may really influence the final product. I've been recently in the Barroso Valley here in Australia, and in one of the most important wine cellars, there is a set of jars, each one with a different kind of soil, to point out the fact that different soils can produce very different kinds of wine, even if the grapes is the same. So the problem is really complex, and the gold standard in trying to identify the wine profile is to use very expensive analysis like NMR or isotope ratio mass spectroscopy. And these are analyses that require very expensive instruments, and also they require very large databases. However, having pluriannual and very large databases is not very reasonable in this kind of task, because it is very hard to get wine samples, because it's not so easy to get the right wine samples, And so we need to exploit something that is the state of the art in chemical analysis and coupled with the state of the art in data mining in order to get something useful. So the challenge is to obtain standard procedure from the chemical point of view with standard instruments available in chemical laboratories and to check whether state-of-the-art data mining techniques can be useful to solve the problem without recurring to a very complex analysis like NMR. The context is the following. We are dealing with a specific region in Italy, which is Piedmont. Piedmont is one of the most famous wine regions in Italy, and we are dealing with some kind of wines that are produced here in a very specific region, which is the Lancashire, and which is a region in the south of Piedmont. Even if we're dealing also with some other kind of wines in the northern part of the region. This region is very important from the wine producers because it has been awarded as a UNESCO World Heritage Site in 2014, and so there is an increasing interest in pushing forward the products and the wines from this region. However, when you buy some bottle of wine like Barolo wine or Barbaresco wine, which are the most important wines in this region, then you must be sure that what you are buying is exactly this kind of wine. This is because one of these bottles may be worth, let's say, hundreds of euros. So you don't want to spend hundreds of euros for some wine which is not what is indicated in the label. Mislabeling is one of the most important fraud that may be detected in this context. The project, the Trackers Wine project, has a target Nebbiolo-based wine. Nebbiolo is one of the the most important grape variety that is involved in the production of the high-quality wines from Piedmont. In particular, the wines that we were looking at were Barolo, Barbaresco, and Gattinara, who are the most important wines for this kind of cultivar. We wanted to exploit state-of-the-art data mining techniques. We don't want to invent anything. We just want to see whether state-of-the-art of data mining techniques may be applied to state-of-the-art chemical analysis in order to get something useful for the wine authentication. We dealt with different wine from different areas and from different wine companies, so we tried to have a kind of variety in the samples that we analyzed. Different typology of wines in the sense that we dealt with commercial wines. I mean, wine that were analyzed by buying some bottles in retail points, and also with model-based wines that were specifically prepared by the wine companies participating in the project to have some samples that may be used for some kind of analysis that I'm going to discuss now. The idea was to exploit what Kirill Wagstaff indicated as one of the, let's say, framework that must be used when you want to introduce data mining techniques in a specific problem. We had to phrase the problem as a machine learning task. We have to collect data and generate features in a suitable way. We have to choose and develop algorithms and to conduct experiments, and then to interpret the results in order to persuade users to adopt the techniques. In this case, the users were, let's say, the Chamber of Commerce in our region. They have let's say, the duty of controlling the authenticity of wines, and they must have some useful tools in order to, and very easy to use tools in order to decide whether something that is subjected to the evaluation is exactly what it is said on the label of the bottle. We submitted this work to the emergency application track because, as you can see here, we don't have big data here. It is very hard to get samples, so we had to deal with just a few hundred samples, 146 samples of wine, divided into different categories. And in particular, we were interested in identifying, what do I say here, HQ wine, which means high quality wines, and in particular, 3 of such wines, 3 of such wines were identified as high quality wines. Then we had some other intermediate wines that were produced with Nebbiolo grape as well. All these high quality wines, are produced by 100% Nebbiolo grape. Even the other here are produced by 100% Nebbiolo grapes. However, we also use some control wines, this Lange wine here and this Gattinara blend here, to check whether it is possible to identify differences between high-quality wines and control wines that may be used to fraud the consumer when they are put in the market. So I can put in the market one of the control wine to say on the label that the wine is Barolo and this is a fraud. It's not possible to do that. So we have to identify in some way whether these control wine are not predicted as to be high quality wine. And we use also some intermediate wine here to, let's say, mix together different kinds and variety of wines in the data set. The analysis that provided the feature to be that describe each case are very common analysis in chemical labs, like spectrophotometrics methods or chromatographic methods. They are not very expensive. It is very easy to get this kind of analysis, together with some other specific analysis that can be performed on a wine sample. For example, the resveratrol content is one molecule that is very typical of red wine, and the resveratrol molecule, it's one of the features that survive feature selection, meaning that it's very important to get to have a value about this molecule in order to identify the right kind of wine. We collected data for having at the end 40 continuous features, which are the chemical parameters. We have missing values in the data for about 1/3 of the samples, especially concerning the percentage of grape. And we get finally 9 wine types, 9 wine categories, among which 3 are the categories that we are interested in as high quality wines. The problem has been phrased as a classification problem because we tested very quickly some unsupervised techniques, and we find out that it's not working very well. And so we switched to testing classification techniques with 9 classes. And the emphasis is not on the global accuracy of the classifier, but instead is the emphasis is on the misclassification of high quality wine with respect to control wine. So we don't want a control wine to be classified as a high quality wine or vice versa. This is the main task. So even if we can measure the global accuracy of the classifier, we are more interested in these latter issues. The data sets were called D1, D2, and D3. In the first data set, we got all the samples with all the features. We used a second data set for all the samples, but with a feature selection method applied in order to reduce the features to 15 features. And then we finally tested also a third data set where we just end up with 13 features, meaning that we use the feature that are selected by the feature selection method by removing also the percentage of grape that are still present in the second data set. We tested different classifiers. However, in the paper, we reported the results from these 3 classes of classifier. We tested the Bayesian net classifier, learned by means of a standard Cooper's algorithm and without the naive Bayes assumption. So there is actually a Bayesian network at the end of the process. We tested a support vector machine based on sequential minimal optimization, and we tested some kernel, and we finally decided to use a Pearson universal kernel. We also adopted Platt scaling because we wanted to have probabilities of predictions in the output. And finally, we tested a multi-layer perceptron with just one hidden layer and with the rule of thumb of using a number of hidden units, which is half the number of features plus the number of classes. We use the Weka implementations of such algorithms, and we end up with some results. You can see here the global accuracy of the classifiers against the 3 data sets. As you can see, there is a quite good accuracy for the multi-layer perceptron and the support vector machine. And however, as I mentioned before, this is not the main measure that we are interested in, because we don't want to test the global accuracy of the classifier, but we want to get insights about the capacity of the classifier of classifying the right way the control wines, which are the wines that may be used to counterfeit the high quality wines. So for doing this, we tested the classifier and against the 3 data sets. And in particular, if you look at this picture here, this is the support vector machine. We have the 22 Langa control wines. You can see that in the data set D1, the support vector machine is able to predict the Langa wine, all the Langa wines as being the Langa wine. The other control wine here are also predicted as the right class here, and the 3 high quality wines are predicted in this way. So you can see from these pictures that against dataset D1, no control wine can be predicted as a high quality wine, and vice versa. There is no possibility of having a control wine predicted as a high quality wine. And this is a first point that must be highlighted. The same happened for D2, where we can see that, again, we have a very good performance of the support vector machine classifier. It's not so good in precision, the Bayesian networks. However, again, the same consideration applies here. The consideration is that no control wine is predicted as high quality wine, and vice versa. Even this prediction here, Barolo wine is predicted as a Barolo wine or as a Barbaresco wine. And these 2 predictions can be reasonable because they are very, very similar wines. So to have this confusion is not a problem. It could be a problem if a Langa wine would be predicted as a Barolo wine or as a Barbaresco wine. And the same happened for D3. So using feature selection and removing all the percentage of grapes inside, we can get the same kind of results, which show that support vector machines are quite robust in trying to distinguish the control wines and high quality wines. To get some more details, this is the probability distribution of the misclassifications for the support vector machine classifier against the last data set. As we can see, for example, the blended wine, which is one of the control wine, has almost zero probability everywhere of predicting a high-quality wine. These three are HQ wines, and there is almost everywhere zero probability of predictions. And on the other hand, high-quality wine like Barolo and Barbaresco, which are misclassified by the support vector machine, have zero probability of being classified as control wine. So it seems to be a very good indication of the fact that we can use these standard chemical features in order to discriminate between inaccurate blending and fraud produced by producers if they want to confuse their wines with H-quality wines. We also tested another category of wine, which we call non-Nebbiolo wine, non-wine. These are wines that do not have any kind of Nebbiolo grape inside. So this kind of wine were not used for training the models. So the model didn't see any kind of such wine in the training phase. We just use it for testing the fact that the model is in some sense robust also to different kind of blends that may be submitted to the classifiers. And again, we can see that the support vector machine is quite robust in this sense because, for example, in the first case, there is a problem here for the Bayesian network classifier that think that one of the sample is a Gattinara sample and is not a Gattinara sample, so there is a confusion of the non-wine or non-Nebbiolo wine with a high-quality wine. Again, the same happens here for the multi-layer perceptron. There is the multi-layer perceptron has a confusion of the non-wine as a high-quality wine in two cases. However, the support vector machine seems to perform quite good in the sense that the wines that are predicted by the classifier are quite reasonable from the point of view of the classes that the classifiers know. Okay. So very quickly to the conclusions. This has been the first attempt to try to exploit standard state-of-the-art chemical analysis for wines coupled with state-of-the-art data mining techniques. In previous work, there is a lot of works trying to exploit machine learning and data mining in wine identification problems. However, usually there are very different objectives. The objective is to identify the wine, and so the global accuracy is one of the most important measures at the end. We don't have this kind of objective here. We don't want to improve the global accuracy. We want to be sure that our classifier is able to help in identifying some kind of wrong or illicit blends, as in the case of the control wine that are produced in different areas with respect to the areas that are allowed to be used for producing such kind of wines, or for the detection of unrelated cultivars, as in the case of non-Nebbiolo wine, the last kind of result that I showed you, because we don't want to have some Barolo or Barbaresco wine to be sold if there is some unrelated cultivars inside, which means that it is possible to produce and to sell bottles of high monetary values without using the right rules and without having the suitable cost in production. Feature selection seems to be quite interesting as a way for reducing the number of chemical analyses that must be used for learning the classifier. The weak point is definitely the reduced number of samples. we just had to deal with 146 samples, which is not a huge data set, is not a big data set. As I mentioned before, it is very hard to get wine samples for this kind of task. However, related to with similar works done in the past, even in the food chemistry field, the number of samples is in line on the number of samples used by other researchers in this area. However, in order to address this point, we plan as a future work either to push forward towards the wine companies to be able to get some more wine samples in the future, maybe by improving their interest in this kind of data analysis. But also we are trying to generate synthetic data, and we have some preliminary results by using a linear Gaussian Bayesian network generator in order to generate new synthetic data from the original wine samples that we collected. Okay, thank you very much.
We've run out of time for questions, so we'll hold them off to the break. So any questions for Luigi?